Alright, good morning guys. We've got 4 handouts today. 2 of them will make up 77 and 2 of them will make up 78. So the 2 that we will be going over together are the 77 ones. And so we are in the second half of this unit. I was finally able to put up some dates of the estimated test day. So looks like it'll be about this time next week. But of course this is a B week, so I'll see you today and tomorrow. So that is how you're going to get caught up with A-Day a bit. Okay, so we've been doing a lot of limit stuff, and today we're going to talk about continuity, which doesn't sound like it has anything to do with limits, but you will see after a moment that it does. So we're going to do these notes together, talk about what the definition of continuity is and how to apply that. Have you practiced that on those 2 pages, the 78. Have you do 1 review Khan Academy assignment and turn in 1 assignment 76 from last class. Of course, if you forgot to turn in 75 when I asked for it last class and you forgot to do it for homework, you need to get that in the next minute or 2. All right. So, what is this, 77? Okay, so this is the one that is 77. This is where we talk about what it means to be continuous and a couple of different types of being discontinuous or not continuous. So I guess I could just tell you the 3 parts that you have to check for continuity, but to try to increase the odds of that sticking in your head, the whole front page here is mostly about trying to discover what the 3 parts are by looking at a few examples here up on this picture. Some of this didn't print off the best, so these 2 are supposed to be open circles, so you might want to emphasize that a little bit more in your graph. But at the top of the next page, I think we'll just come out and say what the 3-part definition is. So again, this first page is trying to help push you into it to help you kind of discover it. But to be continuous just means your graph is nice and smooth, not broken up, no holes there, no asymptotes there, nothing like that. So if I asked you if you thought it was continuous at x equals -2, I would hope that you would say yes. It's a nice connected function there. But to try to push you in the right direction, it is continuous here. Does that mean that the limit must exist at that point? So notice that it approaches, looks like it approaches 2 from the left and it approaches 2 from the right. And if that was not true, if they were approaching different things, then there would be a break in the graph. So I would say yes. If it's continuous at a point, the limit needs to exist at that point. Remember, for a limit to exist, it has to approach the same number from the left and the right. So if it's not approaching the same number from the left and the right, then the graph must have some kind of break in it. Okay, but then question 3, is it continuous at x equals 2? I think that's a little bit easier to see that would be no. There's a hole right here. So even though that point exists way down here, there's still a break in the graph. Now, to compare this to question 2, in question 2, I'm telling you that the limit has to exist for it to be continuous. In question 4, it's asking if the limit exists, does that mean it's continuous? Well, this is definitely not continuous, but it approaches the same y value from the left and the right. So it's required for the limit to exist to be continuous, but just because the limit exists doesn't mean it is continuous. So I would say no. And personally, for explaining my reasoning, you're welcome to do words instead, but I just make a quick little picture here. And I'm going to refer to x equals a today. That's just a generic x value. I don't want to use a number there and make you think that I'm only talking about something specific. Any x value a. So this limit exists, but it's not continuous. There's a hole, yes.
So on the quizzes, we can do that?
Do what?
Like draw a picture to show instead of words?
No. I will tell you when we look at the next page what you'll have to say. You're going to have to state, if you think it's continuous, you'll have to state all three parts of the definition and say that they're true. And if you think it's not continuous, you'll state any one of the three parts of the definition that's not true. I just haven't told you what the definition is yet, so I can't really refer to that. Okay, so again, the limit has to exist to be continuous, but just because it's continuous doesn't, or I'm sorry, just because the limit exists doesn't mean it's continuous. It's not a two-way street there. Okay, if a function is continuous at a point, must the function be defined at that point? So, if this is continuous at x equals a, it's asking, does that mean that f of a has to be there? And I would say yes, because otherwise you would have a hole. If f of a does not exist, you have a hole. And a hole is a break in the graph, which is making it not continuous. So there's part 2. Part 1, from questions 1 and 2, I hope that you see why the limit has to exist to be continuous. And in question 5, I hope you see that the point has to exist. Okay, so look up at the picture above. Does it look like it's continuous at x equals 1? At x equals 1, to me there's a hole there, so I would say it's not continuous. Now what's tricky about this one is, and I'm going to basically draw the same picture down here for my reasoning. Just because f of a exists, it may be way up here instead of down here. So sure, to be continuous at x equals a, there has to be a point at x equals a, but just because there's a point at x equals a doesn't mean it's continuous. A second thing that's not a two-way street. Question. Okay, so now we can kind of talk about, try to summarize these and then write more formally. Again, I'm just trying to help you see why these things are important. So within questions 1 and 2, we talked about for your graph to be nice and connected and continuous, your graph can't be jumping around. So the limit as x approaches a, whatever value you're interested in, has to exist. That makes sure it approaches the same number from the left and from the right. Then a couple questions later, we talked about what happens if there's not a point there. So if you want it to be continuous at x equals a, there needs to be a point at x equals a. And then this last part's the hardest to see. It's coming from this. This example that I drew here meets the first two conditions, but you can see it's not continuous. The limit exists, step 1, plus u. The point exists, step 2, but the point's not in the right place. For this to be continuous, this point would need to be down here. So the limit, whatever it's approaching on the left and the right, needs to be the same as the point. Whatever the y value of the point is, needs to be the y value it approaches from the left and the right. So I think that, I'm not sure, but I think question 9 trickles onto the next page. So the more formal way to say this, instead of just saying the limit exists, we need to see that the limit from the left is the same as the limit from the right. Otherwise, your graph is jumping around. We need the point to exist. Otherwise, there's a hole there. And just because the limit exists and there's a point, if the point's in the wrong spot, like this picture, limit exists, point exists, but if that point's not in the right spot, it's not continuous. So this part we can just copy down. Whatever it's approaching from the left and the right, that y value should be the same as the y value of your point. This, again, I could have just started class with this. I could have just told you that's what the definition of continuity is, but again, the whole front page was trying to help you see why some of that was true. But that is the 3-part definition of continuity. And I would suspect on your next test, we will probably have one question that just straight up asks you, what are the 3 parts? You need to memorize those 3 parts. Now, one other thing I can do for you before we talk about the types of discontinuity, there's a couple different types you need to identify, is I want to make a counterexample to each of these, just because I think it helps you see why they're so important. So if this was not true, if it approached a different number on the left versus a different number on the right, it might look like that. And I think it's pretty easy for you to see why that's not continuous. That's why this has to be true for it to be continuous. If this is not true, it might look like this. If that point doesn't exist, then you've got a missing piece to your graph. Also not continuous. And then finally the third part, the one that's a little bit harder for people to get, but just because the first part's true, the limit exists, and the second part is true, the point exists. If the point is not right here where it needs to be, but is instead somewhere else, that's not continuous. So again, these are counterexamples. If this was not true, it might look like this. If this was not true, it might look like this. And if this was not true, it might look like that. Again, I think you all are convinced that this would not be, these are 3 examples of not being continuous. So I'm just trying to reiterate why each one of those is necessary. Okay, and then the types of discontinuity. There's 3 types that we will ask you to look at in this class, and 2 of them are pretty intuitive. 1, not so much. But jump discontinuity is when the graph is jumping. So notice at x equals 1, the graph quickly jumps up. At x equals 2, it quickly jumps down. Most students remember that really easily because it looks like the graph is jumping, and jump discontinuity sounds like what it is. Whereas infinite discontinuity is when your graph's going to infinity and or negative infinity. So like x equals 4. Same thing, the name infinite kind of gives you a hint that it's going to infinity and negative infinity. So most of the time, that's not one that students would struggle with. But this one, 14, is an important one, and this one is not intuitive. Removable discontinuity is when it's not either one of these, but instead there's a hole there. Now, this just didn't print off the best, so emphasize, if you look real closely, you can kind of see I tried to put it there, but at x equals -2, there's a hole, but it's not called hole discontinuity, it's called removable discontinuity. And that's whether there's a hole there and a point somewhere else, or not a point somewhere else. Either way, it would be removable. X equals 1 and x equals 2 are not removable because the whole function's jumping up. It's not just not existing at a point or just jumping for a point. So that's the one that I would put a star by. Again, not intuitive. The other 2 are a little bit intuitive. You're welcome to X out this part. Even in AP Calculus, we don't have to talk about oscillating discontinuities, but I still like to print it on here so that you guys know someday, you might get to a math class where you talk about this, so it's good that you know it could exist. But if you have a graph that zigzags back and forth fast enough, then that is considered oscillating discontinuity. Again, I will not ask you anything about that. I just wanted you to be aware that that's a thing.
Why is it considered that?
Because if it's going fast enough, the slope of each of those is like almost infinity. It just gets so extremely big or so extremely small as it goes back and forth that it just messes up and breaks.
Do we make a bonus question?
I don't think we have a bonus question on the next test.
Okay.
But okay, so now to pull this together so you can see what kind of questions could you even be asked about this. We got a couple here. We're going to save the very last question for later, honestly only because I forgot to do it in my A-Day class, and I want y'all to be on the same page. So we'll come back and do 19 later. 18 is a reprint of 17, so we don't need to do the same question twice, but we need to do 16 and 17, and we'll be finished up with the notes. So I mentioned to you guys when we started this unit, we do this limit unit at this time of the year for a few different reasons. It gives you a little bit of calculus, which is good for those of you that choose not to do any calculus. And for those of you doing AP Calculus next year, everything we've done is like the first 2 weeks of school, so it makes it a little less stressful that you've seen it all before. But typically in AP Calculus, we do multiple choice and free response because that's how the AP exam is set up. So early in the year, we can't give real FRQs because you just don't know enough calculus. So most years we do something like this for the first FRQ on the test, where it'll say graph a piecewise function. So luckily we have reviewed how to read a piecewise function recently. But some of the time it's y equals negative x squared but you've got to read the restriction. It's only negative x squared when x is equal to 0, which is the filled in circle, or less than 0. So I'm going to keep the left part of this graph and not keep the right part of the graph. The other piece of my piecewise function says that sometimes it's y equals x. So if you can graph y equals x, you graph it. But only keep it when x is greater than 0. So I should keep the parts to the right and not the parts to the left. Now, in past years with pre-calculus, I know students sometimes feel uncomfortable graphing piecewise functions. That's kind of hard for me to understand because, again, all I really did was graph this and keep that part of the graph. And then I graphed this and kept that part of the graph. If you can graph those individual pieces and you know how to read an inequality, then you can graph this. But one tip I can give you is that by calling this f of x, that implies it's a function, and all functions should pass the vertical line test. So if you graphed this on your own and it didn't pass the vertical line test, it couldn't be a function, which is a good sign that you may have done something wrong. Okay, so I think we often ask students to graph something like that, and then we ask maybe a limit question or two. So the limit as x approaches 0 from the left approaches a y value of 0. The limit as x approaches 0 from the right approaches 0. Remember, limits are asking what y value does it get closer to. And if it approaches 0 from the left and 0 from the right, then if it doesn't designate, it's got to be the same. But if it's approaching 0 from the left and 0 from the right, the limit would be 0. All of that to lead up to part D. This is what's different. You've been answering this stuff for like 2 weeks now. Is the function continuous at x equals 0? Yes or no?
Yes.
But, okay, so FRQs in AP Calculus, 9 points each, and then it scales, so it's actually about 50% of a test grade. But sometimes they might give you one of the 9 points for getting yes versus no. But typically you got to get the justification right. So you have to explain how you know it's continuous at x equals 0. And you can't explain it the same way you would explain it to your friends. You can't just say it's connected. There's not a hole there. That's not enough. You have to know that three-part definition. So the first part of the definition said that the limit as x approaches 0 from the left is equal to the limit as x approaches 0 from the right. That made it not jump around. I also have to identify that at 0 there is a point. That's the second part of the definition. And finally, to prove it's continuous, the third part of the definition, not only does the limit exist, not only does the point exist, but they're the same thing. The y value here was 0, and the limit approached 0 from the left and the right. So if you want to prove that something's continuous, if you think it is yes, you have to state all three things. It's not jumping, there's not a hole, and the point's in the right spot. The limit exists, the point exists, and the point is equal to the limit. So to prove yes, you have to state all three things are being met. And of course, if you don't have those three things memorized, then you can't do that part of the FRQ.
Can you explain that one on the right, that rule of the f of x equals f of 0, and then 0 to 0 to 0?
Well, the limit was 0, right? We did that here. The point is 0. When x is 0, y is 0. And these two need to be the same thing.
Gotcha.
Because the point, so the problem is, let me pull up this. This is a counterexample. If you're just meeting the first two, the limit may exist, the point may exist, but if the point's way down here and it needs to be up there, then that's not good enough to be continuous. You need whatever it's approaching from the left and the right to be the same as the point.
Gotcha. So you need all three of those individual rules.
All three of the rules have to work. Okay, and one more so we can see what it looks like if it's not continuous. If we were to graph the square root of x minus 1, this would help if you know what the square root of x looks like. That's a parent function, so you probably memorized that in Algebra 2, but you may have forgotten it. But the minus 1 is going to shift it right 1. And the piecewise function says keep it when x is equal to 1, which would be right here, and bigger than 1. So I really kept the whole thing this time. By the way, anytime you guys struggle, like if you're not sure what that graph looks like, it's a lot more tedious. But if you don't have a calculator, you can make yourself just plug in values. 2 is 1. If you plugged in 5, you would get 2. Like you can make yourself make a table, and if you plot enough points, you can kind of discover what it looks like. Okay, the other times, it's a mx plus b. It's got a y-intercept of -2, a slope of -1, which would look like that. But the piecewise function says only keep it when x is less than 1. So he can't equal 1, open circle, and the less than part is going to be the stuff to the left, not the stuff to the right. Again, you basically just graph each of those, keep this part of this one and that part of that one. And again, it implies that this is a function. All functions pass the vertical line test. So if you graph something that didn't pass the vertical line test, you would know that that couldn't possibly be correct. And to try it again. Okay, now we're going to try to answer the same things about this, but this time as it approaches 1. So the limit as x approaches 1 from the left, 3.
No. Yeah, I see minus 3.
Okay, -3, sure. From the right, it's approaching
1.
0. We're telling you what x value to approach. You should be answering with y values. And if it's approaching -3 on the left and 0 on the right, then that limit does not exist. It has to approach the same thing from the left and from the right. Again, you've been practicing these. Practice a little bit more when we get to the test review. But now, is it continuous at x equals 1?
No.
Right, there's an obvious break in the graph, so I'm not concerned about you getting a yes or no correct. But you have to be able to justify why it's discontinuous mathematically, not just describing it in a nice, convenient way. So we've got the three-part definition of continuity. So the one part that does work is f of 1 exists. So that doesn't help you justify no. There is a point when x is 1. But you could use either of the other two. Bless you.
Thank you.
The limit as x approaches 1 from the left is not the same as the limit as x approaches 1 from the right. So that's enough. If you're just trying to prove that something's not true, you only need to point out one thing that's not being met. If you really wanted to, you could state the third reason instead of the first reason. You could say the limit does not exist and the point is 0. Those are not the same thing. So you could either state the first part of the continuity definition or the third part, but you don't have to state both. The only time you need to state all three is if you're trying to prove that it is continuous. So a few examples of where you really have to know the mathematical background of being continuous to be able to do those justifications. All right, before we move on, is there anything on any of this that you'd like some clarification on? Okay, then, so those 2 pages made up 77. The other 2 pages you picked up are 78. So I'd like you to practice those questions over this topic so that you can make sure that you've got that down or fill in the gaps as needed. I do apologize that some of that did not print off the best, so do your best with that. But part of your work should be checking your answers with my answers on the website. So if you just misread the question or something, you know, obviously just fix it on your homework, and you don't need to lose sleep if you answered it wrong because you read the question wrong. Some of it just doesn't print off the best. So, but I can't, I don't know. I don't have like editing rights to those questions, so I can't do anything about that. So I need you to practice those 2 pages on 78. I will add that if you're not being careful there, it looks like it's multiple choice and it looks like it's one answer. It says circle all that are true. So there can be multiple correct answers on some of those. It's not just pick out one. It can be multiple. Practice that to make sure that you have continuity down. And of course, let me know how I can help with that. That should take you 10 or 15 minutes. Then I have one review Khan Academy assignment for you from something we did like 2 classes ago. Trying to take limits if you're given a piecewise function. So you have some notes. If you want to review that first, it might be a good idea. But I need you to practice that on Khan Academy, please. Likewise, I'd be happy to help you with that. And then the last thing I need from you today is to turn in assignment 76 from last class. I need that by next class, which is tomorrow because this is B-Day. But you should already have that done. I'm just finally asking for it. And you've got the rest of the class to get all of that done. And that's about 70 minutes from now. So you've got plenty of time. So make sure you take care of business. Make sure you understand what you're doing. Make sure you're asking the questions you need to ask. Check your answers. Actually, I forgot to update this. This says the 15th is when we're planning on the test, and I think it's actually the class after that. So,
What can I do to make up what I missed on Tuesday?
the handouts will be over there,
Okay.
but to see what the handouts are and to get the information you need, you'll need to get to the class video.
Okay.
You know where that is on the website?
Yeah. Okay.
And so tomorrow we'll go over the last new topic in this unit, and then we'll have 2 classes for review. The only reason we have 2 classes for review is Ms. Thomas, I think she was out sick one day, so she needs an extra day with her classes. So that's going to get you an extra review day also. So again, that says the 15th, but I think it'll actually be the 20th when you get to your test.
I just realized that I turned in 76 on the 75 assignment.
Okay.
I just fixed it. Can
Okay.
I still get full credit?
Since I haven't graded it yet,
Okay.
you get lucky. But in general, no. You need to double check that in the future. But yeah, I haven't graded them yet. I'm about to.